Hello guys, welcome to my channel. This is Ehsan, and in today's video we're going to look at this diode connected transistor, and later on you'll find out why we call it diode connected transistor. Okay, but before we get started, if you're new here, please give me a thumbs up, hit that subscribe button and also the notification bell. So let's jump into it. This is a NPN transistor which we connected the base of this transistor with the collector. This is base, this is collector, and this is emitter. And now I'm going to draw a small signal model for this transistor and connecting these two nodes together. Okay, so if you remember from the small signal model video, we have this R pi, and this is V pi. This is emitter, which is connected to the collector by this GMV pi dependent current source. Okay, and just for the sake of simplicity, we assume that the early effect is neglected, so the early voltage equals to infinity. So this is the base, this is the collector, and this is emitter. And now I'm going to connect these nodes together to complete my small signal model. And now I'm going to calculate the resistance between these two nodes, between the collector and the emitter here. What is the R seen from between collector and the emitter? And if you look at it closely, you can see instead of 3 nodes device, now we have just 2 nodes device. So we can simplify this with just a resistor. This is the maybe the simplest element in the circuit and electronics. Resistor, just a resistor, because these nodes are just the same. So we have just one node for this between base and the collector, and the other is emitter. So now I'm going to calculate the resistance, and you don't even have to go with the traditional methods, because with the traditional methods you're gonna place some Vx, and here this is the Ix, and you had to use your KVL and KCL knowledge to calculate the ratio between Vx divided by Ix to calculate what is the R. But if you look at closely, you can simply calculate it, but I'm going to use the old-fashioned method, which is this one, and then I'm use some intuition into the circuit to make it so simple to calculate the resistance. Okay, so if you look at closely, and here this one actually I'm going to again I'm going to calculate the resistance between the base and the emitter. Okay, so this is another node for me, and these nodes are just the same. It doesn't matter if you place this as a ground or not. Okay, these are just the same because I'm gonna calculate the resistance between these two nodes. Okay, so here if you look at it, you can use KVL, and by using the KVL, minus Vx plus V pi equals to 0, so Vx equals to V pi. This is the first equation that gonna make our circuit so simple, because now I can replace V pi with Vx whenever I see this. So instead of this, I'm gonna use GMVx. Okay, now I can use KCL in these nodes. For example, let's call this node A. So KCL at node A. Here this is Ix coming through this node, so minus Ix plus what is the current getting out of this resistor in this path? The current instead of V pi, I'm going to use Vx. Okay, so here we have Vx divided by R pi plus this current here, which is GM Vx equals to 0. So by some simplification, you can have 1 divided by r pi plus gm times Vx equals to Ix, and now we can calculate Vx divided by Ix, which is this one, 1 divided by r pi plus gm, and instead of gn I'm just use 1 divided by gm. Why I use this one? Because in this way I can set that what is the resistance, what is the resistance equal to Vx divided by Ix. I can simplify this now. Okay, so by using some common denominators, and I'm gonna make it just the final answer for this one. And here, this is what you can see from there. You can set that r pi is in parallel with 1 divided by gm, and these are just the same. You can calculate it in your own notebooks, and then if you have questions, let me know in the comment section. Okay, and this is the final answer. And if you look at closely, you can set this at the beginning actually, because this is where we seen to the resistor. This is r pi is completely obvious here, but how about the 1 divided by gm? This is the dependent current. Depend on what? Depend on its own voltage. So you can simply set that this is equal to the resistor, which is, what is the value of this resistor? The value of this resistor equals to the voltage across it, which is V pi, divided by the current, which is gm V pi. Tada! V pi is crossed out, and you have left with 1 divided by gm. So this is a really great device and great model for this diode-connected device. And you can always set that the resistance between these two nodes equals to r pi in parallel with 1 divided by gm. And because r pi is beta Vt divided by Ic, and 1 divided by gm is actually Vt divided by Ic, so most of the cases r pi is much greater than 1 divided by gm. So in most cases, we simply said that for the diode-connected device, you can model this resistor by just 1 divided by gm. Okay, keep that in your mind. This is going to make you make your life so much easier when you're going to calculate the small signal gain of the amplifiers, or sometimes you're going to calculate the input resistance or output resistance of some amplifiers by just this simplification. Okay, keep that in your mind and try to recalculate this again, and using these methods, just by looking at the circuit, try to simplify this, because before you're going to through just so much equations, KVLs and KCLs. Okay, this is really great idea to see into the circuit and simplify this if you can. Okay guys, I hope you like this video. If that's the case, please give me a thumbs up, and see you in the next video.